Welcome to the era of autonomous AI agents. For a long time, large language models were like brains in a jar, incredibly smart, but isolated from the real world. You could ask them questions, but they couldn't browse the web, check your database, or run a Python script. That's where AI agents come in, acting as a bridge between the model's intelligence and external tools. Today, we're exploring one of the most powerful paradigms for building these agents, the ReAct framework, which elegantly combines reasoning and acting. To understand why ReAct is necessary, we must look at the limitations of standard language models. When faced with complex, multi-step problems that require up-to-date information, standard LLMs often fail. They suffer from hallucinations, relying purely on their static training data. If you ask a standard model about today's weather or a recent stock price, it will either guess incorrectly or apologize for its inability to help. The model possesses the linguistic logic, but lacks the means to verify facts dynamically against a changing environment. Enter ReAct. Proposed by researchers at Princeton and Google, ReAct stands for Reasoning and Acting. It is a prompting framework that instructs the language model to interleave generating reasoning traces with executing task-specific actions. By fusing these two capabilities, the model doesn't just blindly guess an answer, nor does it blindly take actions without a plan. It thinks about what it needs, takes a step to get that information, observes the result, and then thinks about the next step. It's a continuous, intelligent loop. Before ReAct, the state-of-the-art for complex prompts was chain of thought, or CoT. In chain of thought, the model is asked to think step by step. This significantly improves logic and math capabilities. However, because the reasoning trace is entirely internal, the model is completely decoupled from the external world. If it makes a factual error in step 1, that error propagates through the entire chain of thought, leading to a completely derailed final answer. It is essentially thinking in a vacuum. On the flip side, there were action-only frameworks. These models were fine-tuned or prompted to generate executable commands, like web search queries or API calls, without explaining their logic. While they could interact with the environment, they lacked foresight. If an action-only model hit an error like an API's returning a 404, it didn't have the explicit reasoning capacity to pause, diagnose the issue, and formulate an alternative plan. It would often just repeat the same broken action in an endless, frustrating loop. ReAct creates a powerful synergy by integrating these two isolated paradigms. The reasoning component acts as the agent's internal monologue. It helps the model induce, track, and update action plans, as well as handle exceptions. The acting component allows the agent to interface with external sources, like knowledge bases or Python interpreters, to gather additional information. Reasoning tells the model what action to take, while the action provides observations that feed into the next phase of reasoning. This mirrors human cognitive processes. The core mechanism of the ReAct framework is a continuous loop consisting of 3 distinct steps: thought, action, and observation. This cycle repeats until the agent reaches a final answer. First, the model generates a thought about the current state of the problem. Second, it generates an action based on that thought, which is executed by the system. Third, the system feeds the result back to the model as an observation. This structured loop prevents the model from hallucinating steps it hasn't verified. Let's deep dive into the thought phase. This is where the magic of chain of thought is applied, but in bite-sized, actionable increments. Instead of planning the entire solution at once, the thought phase evaluates the immediate next step. A thought might look like, I need to find the current CEO of Apple, so I should search Wikipedia. Or, the API returned an error. I must have formatted the date wrong. I will correct the date format and try again. Next is the action phase. Here, the model specifies a concrete tool to use and the exact input for that tool. An action is usually formatted as a strict command, such as search Apple CEO or calculator 150 times 42. The language model itself pauses here. The application layer, your Python code, takes this command, parses it, runs the actual Google search or calls the calculator tool, and waits for the result. The model is effectively reaching its digital hands out into the real world. Finally, we have the observation phase. Once the external tool finishes executing the action, its output is captured and injected back into the prompt context. If the action was a web search, the observation might be a snippet of text stating that Tim Cook is the current CEO of Apple. This factual piece of data becomes the foundation for the next thought. By grounding the model in real observations, ReAct drastically reduces the chances of confident but incorrect assertions. How do we make an LLM behave this way? It's all in the system prompt. A ReAct prompt explicitly defines the available tools, their descriptions, and provides few-shot examples of the thought, action, observation cycle. The prompt instructs the model to strictly adhere to these prefixes. It tells the model, you have access to a search tool and a calculator. Use the following format to answer. This rigid structure forces the LLM to serialize its reasoning and execution without skipping steps. Let's look at a concrete example. Question: what is the elevation of the capital of France? Thought 1. I need to find the capital of France. Action 1. Search capital of France. Observation 1. Paris is the capital of France. Thought 2. Now I need to find the elevation of Paris. Action 2. Search elevation of Paris. Observation 2. The elevation of Paris ranges from 28 to 130 meters. Thought 3. I have the information. Action 3. Finish. The agent systematically solves the problem. The true power of ReAct is limited only by the tools you provide. Developers commonly equip ReAct agents with a wide array of utilities. You can provide a SQL database tool, allowing the agent to query user data. You can provide a Python runtime, enabling the agent to write and execute scripts to perform complex data analysis on the fly. You can even connect it to a smart home API, allowing the reasoning agent to turn off your lights based on a complex natural language request. One of the most impressive emergent behaviors of the ReAct framework is error recovery. Because the model observes the result of every action, it can course-correct dynamically. If an agent tries an action like querying a table, and the observation is a syntax error, the agent's next thought might be, my SQL syntax was wrong because of the table name. I will check the schema first. It self-corrects without human intervention. This resilience makes ReAct agents vastly superior to traditional, rigid code scripts. Implementing ReAct from scratch can involve complex string parsing and loop management. Fortunately, modern framework libraries like LangChain and Llama Index have built-in support for ReAct agents. In LangChain, you simply initialize a ReAct agent by passing it your chosen LLM and a list of Python functions wrapped as tools. The framework handles the while loop, the regex parsing to extract actions, and the injection of observations back into the context window. It turns a theoretical paper into a deployable application in just a few lines of code. When benchmarked on tasks like Hotpot dataset requiring multi-hop reasoning, ReAct significantly outperforms both standard prompting and chain of thought. While chain of thought models often hallucinate facts deep in their reasoning trace, ReAct's grounding in external observations keeps it strictly factual. Furthermore, compared to purely action-driven models, ReAct demonstrates a much higher success rate because it plans its actions efficiently and avoids getting stuck in repetitive error loops. The numbers clearly validate the synergy of combining reason and action. However, ReAct is not without its limitations. The primary challenge is the context window. As the cycle of thought, action, and observation repeats, the prompt grows rapidly. Lengthy observations, like large JSON API responses, can consume the LLM's context limit, causing it to forget early instructions. Additionally, ReAct requires a highly capable LLM. Smaller, open-source models often struggle to strictly follow the specific thought, action, observation formatting, leading to parsing errors where the agent effectively breaks down and fails to trigger tools. Despite these challenges, the ReAct framework remains a foundational pillar in the development of AI agents. By teaching language models how to think before they act, and how to learn from what they observe, we bridge the gap between static text generators and dynamic problem solvers. As context windows expand and models become better at instruction following, the ReAct paradigm will only grow more powerful. Thank you for watching, and happy coding as you build the next generation of autonomous AI agents.